Hey friends, I'm Scott Hanselman. I'm here with Stephen Toub, partner software engineer. I hope that you are enjoying the Deep .NET series. Folks seem to like the last one that we did, where Stephen re-implemented await and async from scratch, and we all learned a lot. So we looked at all the different topics that folks were excited about, and LINQ, the language integrated query, LINQ with a Q, is high on the list. So we're going to learn about LINQ in a creative way. Thanks for spending time with us today, Stephen.
Oh, it's my pleasure to be here. And I think it also ties in really well with one of the comments you made in the async await talk, which I think towards the end of the video, you talked about how you always like to learn, have some topic that you understand to a certain level and then go one level deeper. And it made me realize that as we were doing that, I talked about iterators. I talked about this mechanism in the C# language and how it shared a lot of similarities with async and await. We didn't go into it, though. So I thought as a follow-up, it'd be fun to do that one level down and actually see what the compiler does, how that stuff ticks, and then how that directly correlates and goes along with LINQ, because LINQ is heavily based on iterators.
Yeah. Another kind of meta point that has me thinking about how we think about programming languages in the modern time, in 21st century modern programming languages, is that we've got languages within languages. We've got regex within a string within C#. You've got SQL embedded within a string. But then with LINQ, it's language integrated. So we've added keywords to make this thing that feels C#y, but also doesn't. And then you've got ways to express LINQ with a fluent method-based LINQ queries, and then a more language-integrated way. And that's kind of interesting, the way that one might have shoehorned a language into C#, but it didn't feel like it was shoehorned. It was very naturally and comfortably added to the language, where now it's become ubiquitous. And it'll be interesting to see how that's implemented.
Absolutely. Cool.
All right, let's do it.
I've got Visual Studio. And what I thought we would just do is just start kind of level set. What do we even mean when we talk about iterators? Right? So in C#, you can write a method. Right? I can write a method, IEnumerable int, let's say get values. And I can return something from this method. So I could say return array.empty. And array is an enumerable, and so I can return that out of this method. Or I could say return new list of int, and I could construct this with a few values. And I'm just constructing the whole thing. My method is called, I build the whole thing, I return it, my method exits. Iterators are basically a form of a coroutine. So it's not you enter the method, you do everything, and you leave. It's you enter the method, you do some stuff, you leave. You come back, you do some more stuff, you leave. You come back, you do some more stuff, and so on, which is referred to as sort of resumption and suspension. And so I could write this iterator, instead of just creating a single list in one shot that contains all my values, I could say yield return 1, yield return 2, yield return 3. And each time I push this thing forward, I come back into my method and pick up right where I left off. So we could see that if I wrote a little loop here and I said for each int I in get values, and then I'll just write out the value of I. If I run this, we'll get what we expect. My window is still building.
And let's go ahead and zoom in. Whenever you have text like that, just make it as obnoxiously large as possible.
Perfect. Hopefully that's obnoxiously large enough.
That's lovely.
And so we get the output we expect. But what's interesting is if I were to come in here and just set a breakpoint, so if I were just to step into this.
And my first question is, like, how does it know that this was the second time? Is it keeping track of I? And what if there was no I?
That's a great question.
Track of where we are in that iteration?
Yeah, let me answer that in just one moment, because I think it'll be easier after I sort of show the back and forth. So when I sort of step through this thing and I go to get that next value, we end up inside get values at yield return 1. Then we end up back in the caller. So we're hopping back and forth. That gets printed out. I end up back in my method where I left off. I come back out. keep stepping through this, and et cetera. You kind of hop back and forth between these methods. In terms of how we actually do that, well, the for each in C# is itself, interestingly, kind of a higher level construct. Like there's this concept in programming languages of lowering, where you take some higher level keyword or construct and you lower it to other keywords, other capabilities in the language. And for each is just that. There is an expansion for how for each is actually emitted. And so instead of writing it like this, we can instead say IEnumerable of, in this case, int. So that's get values. And then I need an enumerator of int, where I call get enumerator on the enumerable. And this actually expands to using a using block, such that if the enumerator is disposable, it can be disposed when we're done with it. And then into a loop that does enumerator.moveNext, and if it was successfully in moving next, it gets the current item and then prints it out. So this and this are the same thing.
Well, let me ask you this then.
Yeah.
If you were going to lower a high-level feature into a simpler feature, could you not take a yield return statement in a for loop and lower it into like a switch statement?
You could, and we're going to get there.
Oh.
Yeah.
Sorry, I'm just kind of learn with you. I didn't mean to.
Yeah, no, that you absolutely can. Now, not exactly into a switch. There's more. It's not, or rather, not just into a switch. There's a lot more ceremony, as we'll see.
Right.
But you got
could,
the exact right idea,
but not in a generic way.
Yeah, you got the exact right idea. And we're going to iteratively kind of go through this. So this is equivalent to this, and then actually this itself, this using here itself, is this higher level construct. So in reality, that's actually more like this. We're going to have a try, and we'll have a finally, and the finally block will do enumerator.dispose. So this coalescing operator here is basically saying if enumerator is non-null, dispose it.
Yeah.
Now, the reason I highlight this is because your question, how do you end up back in the method? What's actually doing that? Well, it's part of this move next call. So this get values method is when it's producing something that's able to hold on to state, the state associated with where I am. And then if there were any locals here, the values of those locals, which are no longer really locals, they're what's called lifted to this object. And so that state all ends up on this enumerator. And when I call move next, we end up going calling back into this compiler generated implementation of move next, jumping to the right place, having all the data, and kind of continuing executing from where we are. And so we can actually see that.
You're saying that enumerator move next, that's not a generic move next, that's a specific move next for whatever implementation of the enumerator we're talking about.
Exactly. So we have the interface, the IEnumerator interface, which is a broadly, I mean, it's generic, but it's also generic in the English sense. But there's an implementation of that has been provided by the compiler. And we can see that if I come in here and I just say console.writeLine enumerator, I'm going to print out the type of this enumerator. So if I run this, we see that this is the name of the type that the compiler generated for this thing. So there's an implementation behind this that the compiler created. And what we're going to do is do that ourselves. So we're going to write the one that the compiler would have done. And to make it a little more interesting, rather than just having, why is this? Okay. Rather than having this silly little get values, let's actually implement a real method that shows up in LINQ. So one of the APIs that's in LINQ is called select. And really, LINQ is a bunch of things, different things to different people. But one of the mainstays of it is a specification for a whole bunch of methods for doing a bunch of different things. And one of the first APIs you learn about is select. Select in some languages might be called map. It might be called project. It might be called transform. Whatever it's called, you have some enumerable. And here we'll say we're going to go from an input type of T source to a result type of T result.
Let me ground this, if you don't mind, really briefly, for folks that may be joining our higher level talk, our 400 level talk, as we say in the US university system. A 400 level talk is a high level talk. They may be more 200 level, or maybe be beginner or emerging senior engineers. You got lists of stuff and you want to look for stuff. I want 3 of those things in this list of 1 million. I want to select out, I want to project out a couple of things, or I have a list that has a lot of things and I want a smaller list. I want a pipeline of data. It's query language, just like it's a structured query language for a database. In this case here, they want to get some stuff out of a list. Typically, we just, when you're starting out as a programmer, you for loop over the list and you're like, hey, inspect every single one of these. It's very tedious work.
Yeah, I mean, so exactly that. If I had a class called person, and person had a property or a property called name, for example, and then I had an enumerable of person, and I'm just gonna, I'll just use what it filled in. If I then just wanted an enumerable of names and I wanted to get the names of all these people, a really simple way to do that is to just say people.select and given a person, get their name. And now I have an enumerable of all their names. And that's what select does. And now here I'm using the real enumerable.select, which is an extension method. But what we want to do is we want to actually write our own version of it here.
Gotcha. And I also want to call out one other thing. You're a software engineer, you're writing code at Microsoft. Some people were complaining in one of the videos that Copilot they found distracting. I see you move very fluidly through it. Sometimes you like what Copilot's offering you, that ghost text that appears. This is not an advertisement for Copilot. This is how you work. This is your Visual Studio and your settings, your key bindings.
Yeah, in fact, I'm on I'm on dog food or pre-release nightly builds of a whole lot of stuff. And a couple weeks ago, Copilot broke briefly in a nightly build, and it pained me. I found I felt like my productivity dropped meaningfully. And again, I'm just answering the question. For me, it's not about writing code that I didn't know how to write. It's saving me keystrokes. You said something to me probably 15 years ago that I still take to heart, which is if you're going to write something, tell someone something once or write something down, save it and put it somewhere so that you can just reuse it again because you have a limited number of keystrokes in your life or something along those lines. For me, it's very similar to that. I could have written this out, and often what happens is it writes out what I was about to write, and then with a single tab, I get what I wanted. Or in this case, I didn't really know what I wanted, but what it presented to me seemed fine. So sure, from an example, let's go with that.
Yeah. So again, I'm not here to sell Copilot, neither are you, but it's interesting to show how you're using it, and you're still writing from scratch. You're writing everything that we're talking about from scratch. Nothing here is coming out of a clipboard, but you can turn Copilot off for folks that are watching if they don't like it. All right. So you're back in select.
So we are going to write our own select. So select basically takes 2 things. It takes my dog is pawing at me to pay attention to her. It takes an enumerable of the data you want to enumerate over, and then some sort of projection, some sort of mapping function. So it goes from one value. It goes from one value to another, and we'll call that selector. And it does this by for each item in the source, invoke the selector. And one of the great things about LINQ is many of the methods are that easily explained and with the iterators that easily implemented. So it really is just for item in source, yields return selector, selector of item. That's it.
So I want to make sure I understand this. I want to paraphrase this, right? So I'm going to pass in some source, some enumerable of a type, and we're going to call that source. And then we've got a function that's being passed in that in this case here is you define what the structure, that the shape of that function is, but the function doesn't exist right now. But selector knows how to take a source and and return a result.
So I could have an enumerable here of int, and we'll just make this an array of 1, 2, 3.
Right.
And then I could say for each int I in select, passing in that source. And I'll pass in a lambda here, and I'll just do I times 2.
There you go. So there's a nice mapping there.
Exactly. And now if I print out I don't get 1, 2, 3. I get 2, 4, 6. Okay. So that's what our function does. Now, functionally, this is almost exactly what LINQ has. LINQ has a little bit of additional argument validation. So let's try and add that here too to make this a fully functional, semantically equivalent method. And I could try doing that by saying argument null exception throweth null on source and throweth null on selector. That looks kind of neat, right? Kind of nice. So let's try. So if I just use the real enumerable.select, and I passed in, and so let's go, we're going from int to int, and if I call this, you can see we got this exception, value cannot be null, right? What we'd expect. Now let's do my select, and we call it, and nothing. Where to go? So the interesting thing about iterators is the entire body of the iterator is in one way, shape, or form the body of IEnumerator.moveNext. Until you call moveNext, zero code from the body of your iterator is invoked, and we can see that. Let me store this into IEnumerable of int e, and then we'll print out.
Interesting. So you basically got your finger on the chess piece. You're ready to make the move. The move is planned. You know, your finger represents that I know what's coming next, but you haven't taken your finger off the chess piece and made the move yet. And the move next is when the move occurs.
Exactly. So we'll do, so I'm just, with printf debugging here, I'm just showing kind of where we are. And when I run this, we see we print out 0, then we called select, then we print out 1. So we still haven't thrown in the exception yet. Then we call get enumerator, we print out 2. We still haven't thrown the exception yet. It's not until we get to move next that it actually happens. And I highlight this because if you go and look at the source for LINQ or any other operator like this, what you'll often see is the argument validation up front as part of the method, and that method itself not actually being an iterator, and then the code that's here separated out into a separate method. So you'll see something like IEnumerable of t result, and I'm just going to call this impl for lack of a better term, and I'll copy and paste these here. And then this will just return impl source selector. You're going to notice all my squigglies went away. Now if I run this, we see we printed out 0, and then we immediately got that argument null exception because this method here is no longer an iterator. It's just a regular old method. This method is an iterator, and it's not until we call that function, we've already executed all of that code. Great. So now what we're going to do is not use iterators and implement this ourselves. And now to make sure that I'm kind of have a little smoke test along the way, I'm just going to...
Fonts?
What's that?
I said fonts.
Oh, fonts, sorry. I'm going to print out some example just to make sure every time we run that we get the same answer, because there's a really good chance I'll make a typo and I'll get the wrong answer. So I'm just going to have some data source here, and we'll say IEnumerable int source, and we'll do enumerable.range to 1,000, and we'll just create an array out of that. And then I want to print out enumerable.select on the source x times 2, and we'll sum that up. And then we'll do the same with my method here. And we're just validating that kind of against an oracle. Like we're making sure that we get the same answer.
Line 2 would be the LINQ or the enumerable implementation of select. Line 3 is your local select.
Exactly. And I'm just, again, just for all purposes, just making sure that I don't claim that I did something and then I've actually broke it. So now what I want to do, I'm going to call this select compiler. And now I'm going to copy and paste this, and we're going to do our own select manual. Okay. Now, the thing that we need to change is this. The argument validation, we're all good.
Sure.
Now, the first thing we noticed when I printed out a type earlier, right? I printed out the kind of that enumerable, that enumerator.
Yeah, that long generated, this is what the compiler made type.
Exactly.
The type that no one would ever see unless they looked.
Exactly. And we also highlighted that when I call this line here, I'm not actually running any code. I'm just producing some object. So what I first need to do is I need some class that I can return from this method. So I'm just going to write sealed class select manual enumerable. And this is itself generic. And I'm going to create and return one of these. So I'm going to say return new select manual enumerable. And now we're going to play a game. I don't know about you, Scott, but with my kids, I have to make everything kind of fun. So I come up with names. So we're going to play Squash the Squigglies. And we're going to make all these squigglies go away. So there's a couple squigglies here. This one doesn't implement IEnumerable, so we need that to implement IEnumerable of t result. It also lacks a constructor that we need. It's also not generic.
And why was it important to mark the class as sealed and prevent inheritance or prevent it from being?
Good question. For this purpose, not important.
Okay.
I am very used to doing it because, for two reasons.
Well, it's defensive driving, isn't it?
It's defensive driving. Even though the official .NET design guidelines say don't seal your types, people can derive from you. I don't personally agree with that guidance and never have. And I like when things are sealed by default. Unfortunately, for me, it's not the default in C#. So I put sealed on pretty much everything. There is a performance benefit to it in multiple situations. And so it also has a side effect. So there are now analyzers that we turn on for our internal and private surface area that says you have a class here that's not sealed and no one's deriving from it. You might as well put sealed on it. And that way, A, you'll know if anyone tries to derive from it in the future, and you can have a conversation and make sure that's appropriate. And B, free perf. This isn't, I technically don't need that. Okay, so this is still showing me a little squiggly because it doesn't have a constructor. So I'm going to ask it to generate a constructor for me. And personally, I like a different naming convention here. I like my fields to begin with underscores. So I'll clean that up. And now this method is now totally implemented. No more squigglies there, but now we have squigglies here. So we're going to go squash these squigglies. We're just going to play a game of whack-a-mole. So implementing this interface, now I have the enumerable, but I need an enumerator. In .NET, the ability to enumerate something means you have an object that is enumerable, and then for a specific iteration through it, for the act of actually going through it, you tear off an enumerator and you use that to iterate. If you want to do it again, you tear off another enumerator and you iterate through it. Now, there are, interestingly, two different methods here, and that's because IEnumerable, the generic IEnumerable, actually inherits from the non-generic IEnumerable that was introduced in .NET Framework 1.0. Both of them have a getEnumerator method because IEnumerable of t, its one returns an IEnumerator of t, and IEnumerable, it's just returns a non-generic IEnumerator. So we have two of these. But because the IEnumerator inherits from the generic inherits from the non-generic, I can just implement it just by calling to the generic one, and now I only have one thing I actually have to implement. All right, so we're making progress. Now we need the enumerator because I need to do something in this method. We now have a squiggly here that I need to go and solve. This means that I need to return something new here. So I want to be able to say, return a new enumerator, not char enumerator. So I'm going to go and create a new class. This one, again, just my own personal approach and hygiene. I'm defining this as a nested type, and I'm making it private, and I'm making it sealed. So enumerator, this is going to implement IEnumerator, and I'm trying to ignore for pedagogical purposes Copilot because it was probably right, but I want to write this out myself.
In this case, jumping ahead is problematic.
Exactly.
And I do want to call out, because not everyone who's listening may speak English as their native language. Additionally, even folks that are native English speakers may make assumptions about why a thing's called a thing, right? And to enumerate a thing, the word, the num is in there. It's to number something, to count them out. To enumerate it, go 1, 2, 3. Are you the enumerable a thing, or are you the enumerator who is numbering those things? Names matter, and knowing what's behind those names matter. So I really like how you're calling out the differences where you're enunciating. It's important for us to remember that this isn't just a word that programmers made up that didn't exist before. To enumerate things is to count them.
I love that call out. And as I think you highlighted when we were talking about async await, naming is one of the hardest problems in computer science. So we spend a lot of time thinking about these names. Exactly. We get it right most of the time. We get it wrong a few times.
What is it they say about computer science? There's the 3 hardest things are naming and off by 1 errors.
Yeah. So we're creating our enumerator, and we need to kind of forward all the information along. So we're going to pass the source and the selector into our enumerator, because effectively the enumerable and the enumerator are the same thing, but we can get any number of enumerators from the enumerable. So we'll pass those in. This also needs the stuff stored in fields. Oops. Also needs it stored in fields. So we'll do that. Okay. But so now we no longer have a squiggle up here, but now we've got our squiggle here. So we're kind of getting down to the meat of it now. So now we have our enumerator, and I'm going to implement this interface. And there's now a bunch of interesting things here. Some of them I can just get rid of right away. So let's go ahead and
zoom in again. I'm going to keep reminding you of that. And we're going to have to pause because we're going to want to think got complicated really fast. Hang on a second, Stephen, you're moving so quick. Right? Let's do a level set here. Let's return to the top very briefly and remind ourselves of where we're at and why did we get big fast. What are we trying to do is to get rid of those squigglies to make select manual do what select would do. We're re-implementing that select from scratch. And in chasing the squigglies, you're making sure you're meeting all of the expectations that are being imposed upon you by the compiler.
Right. Effectively, the compiler and the Visual Studio are showing me where I'm violating a particular contract. And when the squiggles go away, that's a pretty good indication to me that I've at least met the contracts that it's able to see for me. It can't necessarily see the behavioral ones, but it can see the ones that are sort of statically visible.
Exactly, because in a previous world, 20 years ago, 25 years ago, those squiggles would be the result of a compile. So if you were doing this in Vim or Emacs with black and white and no color, you'd make the change compile, make the change compile, make the change compile. So I'm watching your inner loop, the Stephen Toub developer inner loop work here as you're using that as a hint to indicate that you're heading in the right direction.
Exactly. And we talked about this, there are various forms of this. I mentioned when we were talking about async await that I really like the color coding in the colorization. And I use that colorization as an indication. So if I see a field that's grayed out, why haven't I used that yet? And is that something I need to be thinking about?
I also like the analogy of Word, Microsoft Word, where a red squiggly is spelling error, but a green squiggly is grammar error. Well, and similar things here.
A very similar thing here. You can notice I've been ignoring this green squiggle. I've been focusing on the red squiggles. This green squiggle is just, you've written something that hasn't been used yet.
Yeah.
So I'll get to that later because I don't care about that right now. But to your point of kind of figuring out where we've been. So we had our method. Our method creates an enumerable. So we implement that enumerable. Our enumerable creates an enumerator. So we implement that enumerator. And now we're down in sort of we're iterating through this sequence of data. How do we do that? And we have to implement a few things. Now, some of them are super easy. I showed how because IEnumerable of T inherits the non-generic IEnumerable, that we could implement its non-generic get enumerator in terms of its generic get enumerator. We have the same thing here with IEnumerator. IEnumerator of T inherits the non-generic IEnumerator, which means it has two currents. It has the generic current and the non-generic current. So I can just implement the non-generic current in terms of the generic current. Now, there is an interesting squiggle here. You brought up nullable reference types in the last conversation. And I mentioned that there are some places where it's not 100%. It's really good, but there are a few places where around the edges, not always perfect. So this is an interesting case because the compiler is saying, all right, you've got something here that's typed as a non-nullable object, but you're returning current, which is just a generic T result. And there's no constraints on what T result could be.
Right. No one ever said T was allowed to be null. They just said it could be anything.
It could be. Someone could have said, I want to select nullable strings, and therefore this could be a nullable thing. So it's telling me, just FYI, like you're trying to return something here that you've said will never be null, but it might be null. Now, the reason that this is interesting, and I said, we there's some things around the edges, is because Enumerator, the non-generic interface based on object, has been around for 20 plus years, 22 years, I guess, at this point. And it has always been able to return nullable things. And because of how it integrates with for each, it's very difficult, if not impossible, to come up with what this type could be, because it might be nullable, it might not be nullable. And we couldn't decide what it should be. So I can actually, normally if I were to change something from, as part of an interface, from non-nullable to nullable, the compiler would yell at me, but it doesn't. And the reason I could type either object question here or object is because if I go and look at the definition for Enumerator, it's not actually showing up here. Let me bring up.
This is a great reminder to folks that the .NET website, which is dot.net, has some subdomains on it, and one of them is source.net, which might be hard to say, but is easy to remember and type, and it is available to you. So if you ever want to look for the source code for .NET, you can do that.
So this is the really interesting part.
Wow.
The vast majority of the core libraries are annotated for nullable reference types. Everything is just pound nullable enable at in the project at the highest level. But every once in a while, I can probably count on one, maybe two hands, places where we just couldn't figure out what it should be. And so around just those things, we have disabled nullable reference types, leaving this what's called oblivious. So current could be nullable, it could be non-nullable, doesn't matter. Yes, and as a result, you can do either here and the compiler won't yell at you. The other thing I could have done here is use that fun null forgiveness or null suppression or damn it operator we talked about last time.
Current, and I mean it. Exactly. I know what I'm doing. I know what I'm doing.
Yes. I don't care. All right, so we've got that. I'm going to empty out dispose for now. Dispose will populate as we need to. The purpose of dispose is just to clean up any resources that we might find along the way. So if I have any disposable, the things that are themselves disposable, we're going to want to add something into dispose to take care of that. Move next is the big one we need to implement. Reset is interesting. Reset is largely a legacy thing that came about because of .NET sort of ancestry with COM. Reset basically allows you to have an enumerator that you reset to the beginning of the sequence, and then you can go through it again, and you can call reset, and without getting a new enumerator, you can use the exact same one and reset it. 99.9, I don't know how many % of enumerators in .NET throw not supported exception from reset. And this is documented as something that you can do, which basically means that you can't trust reset on any enumerator unless you actually know how it's implemented. And so for ones where they're actually implemented, there's usually docs saying you can call reset and it's okay. But there's the vast majority of them, including every iterator, the compiler, every iterator-based enumerable the compiler generates for you, it throws not supported exception from reset. So we're going to do the same thing.
Okay, makes sense. As long as it's okay. Sometimes when implementing stuff, you don't think about that historical context and that it is there for reasons, but it's very rarely used.
Yeah, and every once in a while, there's real possible value for it. Like if you were really trying to optimize performance, maybe rather than getting a new enumerator where you'd have to allocate, you might be able to hold on to one and reuse it. And so in those situations, maybe you would implement reset. But in general, because you can't trust because it might throw or is likely to throw, no one uses it and no one implements it. Cool. All right. So let's keep going. So now we actually need to start getting into some state here. So we have current, and current needs to do something. In every iterator the compiler generates, and in most of the ones, if not all of the ones in LINQ, current is implemented just by having a field. In this case, it would be t result. We'll call it current. And then the property just returns the field. So yeah, there's that. And now you would notice there's another little squiggly here, again, having to do with nullable reference types. The compiler is saying, well, someone might construct one of these things, and t-result might be a non-nullable, or might be a non-nullable thing. But because everything in a new class is zeroed out, this will start life as null. So I'm getting a warning on the constructor saying, current, you haven't assigned current. It's gonna always be null, even though
saying by the time you exit the constructor, this may not be in the state you're expecting. So you either need to tell me what you mean,
exactly,
or do something about it.
Now, in this particular case, I don't have anything meaningful to assign it to, so I'm gonna shut up the compiler again, and I'm gonna do that by assigning it explicitly default, which might be null, but it gives me something that I can hang this null forgiveness operator off of. Okay, great. So we've got current. Now we have the hard part. Now we need to do move next. So I'm going to come up here and I'm going to copy this implementation that we had right there. And I mentioned before that all of the logic associated with the body of your iterator ends up in move next. So that's how I'm starting. And all of this logic somehow needs to be preserved as part of this move next. So we're going to start by doing the same basic expansion that we saw before. So this was...
Let's go ahead and zoom in on that scope then.
There we go. Good? All right.
Yes, sir.
So we need to expand for each the same way we did before. So I'm going to have using Enumerator of tSource, and that would be get enumerator. And then this will be while enumerator.moveNext. And then this is enumerator.current. So we've done that sort of initial expansion. We can also expand out this using. So this becomes try. This becomes finally.
Making it unambiguous what's happening here. Removing that using, which is a bit of syntactic sugar that hid that try finally.
And it's important not just for pedagogical purposes, but also because I need to figure out what to do with this try finally block in something where I'm going to be legitimately returning out of the middle of this thing. So what does that mean? So you talked earlier about what does yield return lower to? So now we need to figure that out. So for now, we've got this yield return here. First, we already have our current field. So I'm going to store, because I'm yielding out, and let me just put this in a comment there so we can remember where we are. So I'm storing this into current. And now that I have something, move next needs to return true. Right? And if I'm returning true out of this doesn't even need to be a while. This could just be an if block. That also means that when I get to the end here, if I end up down here, it means there was nothing else because move next returned false. So I'm done my iteration, and here I can also return false.
So you're lowering and lowering and lowering to the point where you're using as few keywords as possible that we've been using for the last 20 years.
Exactly.
To really understand what's
because
happening.
From the compiler's perspective, it needs to get down to sort of the nuts and bolts that it can directly emit IL for. And it could emit IL, customized for an iterator, but if it can instead lower it down to things that it already knows how to emit IL for, then it doesn't have to specialize it for this thing up here. It can just lower it in an optimized way to something that it already knows how to emit optimized code for. Okay, so a couple interesting things here. First, is this guy right here. The moment we return, this local goes away. And yet it needs to be the case that when we call back in, our state is preserved. So there's two kinds of state here. There's the state for any locals that I actually need to, I used the word earlier, lift. I need to lift these out. And then there's also the state for where I am. So let's do the first one. So lifting it out, it's called lifting because I'm taking it out of where I am and I'm putting it somewhere higher up. In this case, I'm going to take this and I'm just going to make, up here with my fields, I'm just going to make a private field called Enumerator.
You're giving it more scope. You're letting it live longer.
I'm tying its lifetime. Exactly. I'm tying its lifetime to that of the enumerator. And then down here, I'm just going to assign into that field, and all of these then are in terms of that field. So now my enumerator will survive out of this. Of course, now that it survives, I need to clean it up somewhere. So I need to come down into here to dispose. And down here in dispose, I'll say, if I have an enumerator and I'm being disposed, also dispose this thing. That also means that this here is problematic. I've got this try finally block, but the moment I return, remember, finally blocks execute when you exit out of them, regardless of whether you're exiting out of them successfully or due to an exception. So the moment I return here, I would be disposing of this. That's not what I want. So instead, what I'll do is let me just change this to a catch. And because this code is now duplicated in my dispose, I'll just call dispose here. And then I'll rethrow that exception using throws. This is basically saying whatever exception I'm currently currently handling, allow it to keep propagating.
Right. And this has got a bit of a little side note here. This is one of those legendary mistakes that people will make is they'll go throw E or throw EX. They'll think they're rethrowing, but they're resetting the resulting call stack. Throw by itself maintains all of that so that you can debug it later up.
Exactly. Throw and throw
Don't
E
do that.
Are two different things.
Yeah.
This one will overwrite the stack trace. And in fact, we can see that there's an analyzer that's running, providing static analysis saying, yeah, you sure you want to do that?
I could have used that a long time ago.
I don't remember when we added it, but it's quite a handy little thing to help protect you. Okay, so we're getting pretty close. We've preserved all of our state, right? We come in to move next. We call, get a numerator, we push it forward. If we got something, we return. Otherwise, we return true. Otherwise, we return false. But we're kind of starting over every time we come in, right? We're starting at the beginning. In reality, we need to be able to pick up where we left off. And that we need to keep track of where are all the places we could possibly suspend and resume. And if you give it a little bit of thought, you quickly realize that there's really only two things you need to care about. You need to care about the first time you come in, so when you're at the beginning, and then you need to care about every yields return. Anytime you have a yields return, you might, in the code, you might possibly need to be able to resume immediately after it, which means you need a different state, a different ID or label or something for each of those locations where you yield return. Now I have one yield return and I have one beginning of my method, which really means that there are only two states that I need to care about. So I'm going to come up here and I'm going to add one more field and I'm going to call this state, and I'll initialize state to be 1. That's arbitrary, but I'm just choosing to say that my object, when my enumerator is ready to go and created, it's got a state of 1. And then I'll say, all right, state 1 means that move next hasn't been called yet. So when move next is called and state is 1, that's the first time. That's when my iterator is actually being invoked. So I'll just say if state equals 1, do this. Once it's been invoked, I no longer want to be in that state. I want to be in the next state. So I'm going to say that next state is 2. And so I'll update my state. And this is what's called the state machine. If you picture a state machine as a machine in sort of the computer science sense, which is you might think of as a graph or might be called an automata, but a graph where every node in the graph is a different state. And you process something there, and then you progress to the next state. You kind of follow one of the edges by changing your state number. So I'm changing
the state number, in this case, you're just using it as a number that's not the other number.
Exactly.
Ironically, you could make an enum, which would overload the word enumerator or enumeration. That could be potentially confusing to folks, because an enum in that context also enumerates things, but would be confusing in this bit of context. Are those just magic numbers, 1 and 2?
For me, these are just magic numbers. I'm just counting up. I started at 1 as a nice logical place to start. And then every yield return I have, I'm just adding one more state. In my example, I only have one yield return, so I end up with 2. But if I had a second yield return, I'd have 3. And if I had a third yield return, I'd have 4.
Okay, and that's important because the number of states has nothing to do with the data type. It has to do with the number of states, the cyclomatic complexity, as it were, of that method and how many ways out there are. And
this is also interesting because if you were to look in a debugger, you can kind of, if you look at it, the object produced by the compiler of the enumerator, you can look at the state and say, oh, I know where you left off. You were at the third yield return because I see that number in your state. You can do the exact same thing, interestingly, with async, because again, they share the same mechanism. Every await is equivalent to yield return, as we saw in the last. So each await has its own number. And in general, as a little handy debugging tip, if you ever are debugging, you're doing a real deep debugging session, and you're looking at a heap dump or something, and you've got an async state machine, and you see that the state for the async state machine is 4, count down to the 0-based fourth await in your method, and that's where it is. Because they're just kind of top to bottom of the method in general, wave my hands a little bit, but in general, top to bottom of the method in lexical order, just numbered starting from 0. Anyhow, so now we just need to say we only want to do this code here if we're in state 2, or really this code here if we're in state 2. Because the only other state is we're done. We haven't got to that one yet, but if we're done and someone calls move next again, even though they shouldn't, if someone did, we don't want them to execute any code again. So we'll just say if state equals 2, then do this. All right? And then I should probably also clean up before I return false, just so that kind of when I'm done iterating through, if someone forgot to call dispose on the enumerator, I handle it here. And then as long as I'm doing that, I'm just going to set state to an invalid value, one that doesn't match any of my other states. Because if someone did call move next again, I wouldn't want them to execute any of this code. I just want them to jump right down to the end of the method. And you had a very prescient question earlier, Scott, when you asked, does yield return just translate down into a switch statement? This looks a whole lot like a switch statement just expanded out, but I could just write it as I want to switch on state, and this will be case 1. This will be go to case 2. This will be case 2. And now I have that switch that you asked if that's what yield return lower down to.
Got it. And people can feel some kind of way about go-tos. The only difference is about go-tos and why one person might dislike it and why another person might not like it is that there's the ones you can see, and then there's the ones that you choose to ignore. And, if you don't see a go-to, they're still happening. You're just not seeing them happen.
Exactly. In this case, this is just the syntax in C# for how you move from one case to another. It's not super common, but in this kind of state machine, it's very common because I don't want to duplicate this logic up here. I just want to just copy it down. The other interesting thing to note is I'm not updating in here. I'm not updating my state because when I come back in, I still want to be in state 2 because I want to keep growing. So with any luck, we have now fully implemented. What is this telling me?
So your fonts are really small. So what you're doing, and it's okay that your fonts are small because what Stephen is doing here is he's taking the 20,000 foot view. He's zooming out intuitively to go, have I missed anything in my re-implementation of this? Because I assume then you're going to go and compare it with the implementation that .NET includes and see if you did better.
That's exactly what I'm going to do. So I'm just zooming out. Don't pay attention to the code, but we can see there are no squigglies other than the one for my select manual up here. So I'm just going to write one more line here that is select manual. And with any luck, when I run this, build succeeded, window, we get the same answer across the built-in LINQ, the iterator, and our own manual implementation.
Okay, so we've been doing got here debugging, and we've been doing a very much kind of like see where the wind is blowing. It looks like it's probably fine. There's no unit tests here. I suppose we could see if it's faster. Do you benchmark this in some way to feel like you accomplished something?
That's a fabulous question. I love it. Let's benchmark it. That's a great idea. So, so there are actually two different. Let's do two things.
Well, when I say benchmark, I also mean speed versus like efficiency, which is
exactly.
A totally different thing.
So let's do because I have done one thing that is different from how the compiler would do it, and I'd like to fix that. So before we benchmark, let's profile.
Good point.
So I'm going to take. I've got my enumerable range here, and I'm just going to take this the object that the compiler, the iterator the compiler generated, and I'm just going to say for I equals 0, and I'm going to choose some really large number like 10,000, and I'm going to call this method that many times, and I'll just for each it. So I'll say doesn't matter for me. I'm not doing anything with it. What I want to do is I want to run a profiler. I want to see what happens. So I'm just invoking this a bunch of times.
Zoom in. Don't forget to zoom in and talk to me about that underscore, that unusual use of an underscore. Is that just a habit?
That's habit. So this is totally fine. But C#, I don't know, 8, 7.3, 9, somewhere in that
6 years
area. Added the ability to add a no-op character. That's just a number separator. Just to be able to visually see, it makes no difference. The compiler throws it out when it parses it.
Yeah. Because some people use commas in some countries, and some people use periods for thousand separators, but that is a culture variant thing, and a comma or a period here would not be the correct thing to do.
Right, and this is just the C# syntax for saying, ignore this. It's just a separate. I could put them wherever I want. I could put one here, and the compiler, it doesn't change anything about the semantics of the program.
Nice.
But it helps me to be able to look at it and say, oh, this is 10,000, because I don't have to count the zeros as much. I can kind of visually see that this is 10,000. So to profile this, there are multiple kinds of profilers, and there are profilers for throughput and CPU. There are profilers for I/O. The profiler that I want to use here is for allocation. So I'm going to go up to debug, performance profiler, and select .NET object allocation tracking. And by default, this is going to keep track of every single object that is allocated from the moment, .NET object, managed object, that is allocated from the moment the program starts until this ends. So I run this. The program, it quickly popped up and exited over here. And now it's doing a little bit of analysis, gathering the data, and it's going to present it to me in a manner that I can consume. So I don't know if I can't zoom in, unfortunately.
This is an interesting one. So there's multiple ways to zoom in on this. Do you have sysinternals installed?
I don't at the moment.
Can I give you a trick real quick, if you don't mind? Bring up a terminal and type win-get install sys internals.
All right. Terminal.
Go ahead and pop that up, and we'll give this be a nice little moment for the folks to watch as well. You could use one of your existing terminals and open a new tab as well.
Yeah, let me just, there we go. Just put it somewhere that's fine. All right. Here we go. So win-get.
Win-get install sys internals. And then it'll go and update the database. It'll grab it. It might, if you've never done this before, it'll say, are you cool with this? You say yes, and you'll never say it again. It's going to go and grab win-get. It's going to go and grab, rather, sysinternals, which we all love anyway. One of the things within sysinternals is zoom it. Now, there is a magnifier that's built into Windows itself, so you could right now, don't do it, but you could hit Windows Plus, and it would do a full screen magnifier, kind of like turning on all of the high level accessibility things. But the great thing about Zoom It is that Zoom It will just take a screenshot and zoom in on it. And then you hit escape and it backs right out. So that's kind of what we're going to need for this moment. This usually takes seconds. I'm a little surprised that it's taking more than seconds. So we might have our friend James, who's listening to this, edit it.
To the magic jump forward.
Magic jump forward 10 seconds here. It literally is supposed to take like 5 seconds, so something is up. It won't hurt your machine, though.
Ah, there we go.
Promise.
That's the faith I have in you, Scott.
Trust me. Now run this as sudo. It'll be fine. Format C:/Q. It's very likely that the reason that this is taking longer is that you haven't spent a lot of time in the Windows Store, and it did some Windows Store housekeeping. There you go. So then just go to the Start menu and type Zoom it. It'll run in the tray. It will do nothing. It'll pop up and you'll hit OK. Okay, so hit OK. Now go ahead and minimize that and then point at the thing you want to show me and press Control-1.
Ah, all right.
And then move your mouse around, and then when you're done, hit Escape.
Perfect. Okay. So what I wanted you to see is, because we did 10,000 iterations and we were doing stuff per iteration, anything below 10,000 we're ignoring. It's other stuff that happened during the process lifetime. A lot of it happening at startup. And you can see how much stuff happens at startup. Now, some of that is because we are profiling. There's a little bit of a catch-22 here, a Heisen profiling, I guess. A lot of this allocation wouldn't show up if we weren't profiling. However, the interesting part is anything that is 10,000 or above. And we see that there are two allocations here because if you divide by 10,000, there are two lines here that would have one each. We have an enumerator for this array. So we're calling get enumerator on the array. And then we have that object that the compiler created to represent our enumerable or our iterator. So let's do the same thing now, but instead of using select compiler, let's use select manual. And I'm going to use Shift Alt F2, which reruns the exact same profiling session.
Nice. Nice tip.
And I will do the control once it comes up.
Yeah, this is a really great example also where Visual Studio really shines. You know, we're doing... There we go.
Control 1.
Control 1.
There we go. So, sorry, you were saying, Scott, this is an example where VS shines.
I'm just saying that the profiler is where you kind of go from like, I'm using a text editor and I'm jumping into a terminal, and now I'm in the cockpit of a 747 and I'm really getting some really deep information here. We also see that those allocations are round numbers, which makes them not Heisen profiling things like some of the other random things.
And that's why I have a habit of choosing some large, easily identifiable number like 10,000 or 100,000, whatever, so I can kind of sort out anything that's lower than that and just focus on the interesting stuff.
So I'm immediately struck by the difference in the number here. It was 72 before, and now it's 32. Your average byte size is smaller, and the bytes allocated is less.
But there's now an extra object. Notice that there are now three things that are 10,000, not two. There's the enumerable and the enumerator. We see the top line is the enumerator, then we have the enumerable, and we still have the array enumerator below that. So somehow our custom iterator has ended up with an extra allocation beyond what the compiler generated one has. So let's fix that.
Okay.
Now, why was that happening? Well, the compiler plays a neat little trick. It says, you know what? I've got a perfectly good object here for this enumerable. What if I could just reuse that as the enumerator as well? And then I'm going to come in here and I'm just going to delete the extra nested type that I have. Now everything is just sitting on the enumerator. Now I actually have some duplicated fields as well, so I'll get rid of those. They move all this state up to the beginning so we can all see it. And then instead here, this will just be this. We can get rid of the cruft again. Notice no more squigglies, no more red indicators. We've got our enumerable is implementing both the enumerable and the enumerator. And here we're returning this, which means we're no longer doing that second allocation.
Right, you are your own enumerator.
I am my own enumerator. And if I put these things back and comment this out, and run it again. We'll see we still get the same answer.
Okay.
But let me just change this ever so slightly. Let me take this, and let's just call this M. And then I'm going to say m.sum.
Right.
And I'm
so
going to do it one more time.
Implementation. You're going to be able to break point if you want, I guess, there.
You're
doing it twice now.
But I'm doing it twice. And I'm doing it twice to show that, oops, the second iteration.
Hang on. You've broken it, right? So now you have, but you can't reset because you didn't implement that.
Exactly. But if I were to do the same for the compiler, so let me just what did you say? Control Z to glory? Is that what you said last time?
Z your way to glory.
Yeah, I love that. If I do this for the compiler, the iterator one, and I'll do the exact same thing. I'll say I'm going to have 2 of these, and I run it. This one works just fine.
Uh-oh.
So why is that? Well, the compiler recognizes that just returning this is fine for the first use, but not so much for the second use. So effectively, instead, it adds one more state. So instead of starting at state 0, let's start at instead of starting at state 1, let's start at state 0. And then in get enumerator, I can say if state equals 0, then return this. Right? And also change the state to 1, because that's what this enumerator expects. If it can't, well, I'm going to have to new select manual enumerable t-source.
You will have to make another one.
I will have to make a new one. I construct it with all the same stuff, and I also put this one in the same state that that it needs to be. And now, if I go back up here and I do the can't control Z to glory, then I'll eliminate all of my gloriness. Let me put this back. And if I do
this does make me feel like the magic numbers are hard to keep one's head around.
Well, the beauty of it is that you don't have to. The compiler does it for you.
I see.
And the compiler has no trouble keeping track of this stuff. Now when I run this, now even with hours, we get the right answer. The first
So now
one,
you can do it n times.
Now I can do it n times. Now, there still is a small difference here. And this is a historical artifact. And I think if we were doing this again today, we would not do what I'm about to say. But 20 years ago, some, probably for good reason, well-intentioned folks decided that someone might want to store one of these enumerables into some shared location. And then any number of threads at any point might want to come along and iterate through this thing. And if they did that, this is not safe. If you had multiple threads calling get enumerator on this enumerable at the same time, they might both read state as 0 and both think that they were the first ones there, and then both set state to 1 and both return this. So the actual state machine that is generated needs to do this in a thread-safe manner. And as a result of those decisions, the compiler still does that today, and LINQ as well, because in any situation where LINQ doesn't use iterator but does it manual, and we can talk about why it might, it also provides a thread safety guarantee here. It's not one that I would like anyone to take a dependency on, but it's there because if we were to remove it, we would almost certainly break a whole lot of code somewhere in a very silent manner. So there are 2 ways that we could fix this. One is we could use an interlocked operation. We could say interlocked.compareExchange, saying I want to set state to the value of 1 only if it's still 0. So we could do that, and that would be fine.
Mm-hmm.
Or we could do what the compiler actually does, which is it adds another field here, and it initializes it to the ID of the current thread that was constructing this object. And then here it says if the thread ID equals the same one that created it, and the state is 0, then it's mine.
And that's interesting. You're right. And then on 59, that doesn't need to be locked or anything. It's just a check. It's either reality or it's not. There's nothing to put your finger on. So there's nothing to worry about there from a thread.
Because at this moment in time, there's only one thread that this could be, and it's either me or not.
And I realize it might be ignorance on my part, but my first reaction was like, you should probably put a lock around that. I'm like, well, no, you don't, because you're just passively looking at something that is not going to change its reality. And we're either in the right parallel dimension or we're not.
And your comments are spot on, because we actually have this debate probably once every couple of years about how we should implement this. Ideally, we wouldn't have to implement it at all. But there's the interlocked approach and there's this thread ID approach, and they both have pros and cons. This one is super cheap. It's effectively
free.
It's basically free, but we have an extra field, which means that on 32-bit, this is always increasing the size of the object. And in 64-bit process, sometimes it's increasing the size of the object, depending on what other fields are there. So it might be making this a little bit bigger.
And this is where it gets overwhelming sometimes. I get an analysis paralysis. I can only assume that you all who are working on this low-level stuff seem the same, because at the high level, most .NET programmers are just making objects and like, woohoo, I'm making lists and stuff. But you're always thinking about, but what if they do it 1 billion times? And then you're thinking, because like I'm looking at line 59, I'm going, okay, what registers are this going to be in? What Intel or what AMD op is, what operate, how many cycles is it going to be? Like, you're thinking about that stuff. Knowing the full stack is overwhelming.
Exactly. And your comment about doing it 1 billion times is very much the layer that I spend most of my time in. If you read the perf posts that I write once a year, a lot of the benchmarks or micro benchmarks that I show are measured in some number of nanoseconds, which if you do that once, who cares? Like, it doesn't matter. But for the APIs we're talking about, millions of applications run those lines billions of times, and it adds up.
And that can't be overstated. And this is why folks who are watching and learning about this stuff, like, someone cares about this, and we all should be happy that someone cares about this. How much you, the developers who are watching, chooses to think about performance is up to you. But when you think about how when Stephen and the team removes 10 milliseconds from something, or even less than milliseconds, Bing, that uses .NET and then goes, we just upgraded from .NET 7 to 8. And then you see their graph just drop like this. That is X milliseconds times billions. And it adds up to literally fewer servers that they have to buy. It's real money, and it's real, environmental impact. It's pretty cool.
It's real money. Yeah. Now your point about, the lower levels as well, I should restate if I didn't already say it. Like, I don't actually want most people writing the code that's on the screen.
Of course not. Right.
We're just
learning how to drive stick shift here. We're learning how to drive stick shift. You can choose to take an Uber, but we like to drive stick today.
Exactly. I'd like to do a time check with you, Scott, because there's some interesting places that we could take this, and I don't know how much time.
So right now, I think we've been going for an hour. I think an hour to an hour and a half is where the attention span of the average YouTube viewer starts to wane. I think that we had talked about 2 kinds of benchmarking.
Yes.
So this was allocation based. Why don't we do a bit of little light benchmarking, and then we'll call it, and then we'll return for an even deeper dive, because we need to go beyond in the future. In the next video, let's go beyond select and into where, and keep implementing LINQ.
Awesome. So let's do that. So what I want to do now is we want to
zoom. Yeah, pick your zoom level for me.
Yep. We want to do some benchmarking, and the standard .NET tool for benchmarking is benchmark.net. And so let's bring in benchmark.net. So I'm going to go to dependencies, manage NuGet packages, and I will search for. You can see it's something I frequently do. benchmark.net, and all I do is I just add it into my project. What benchmark.net provides is a library that I can make a few calls into and kind of set up my class, kind of like unit tests. And then when I run my program and invoke a function in benchmark.net, it goes and it builds multiple copies of my projects in an optimal way to be able to measure the code that I want measured, and do a lot of statistical analysis to then provide me with very precise information about what it costs. So,
and shout out to Andre Akinchin, who's a perf engineer at JetBrains, who is the maintainer of benchmark.net.
Yeah, he's wonderful, as is Adam Sitnik, who's also one of the other maintainers, who is now actually on the .NET team. So I'm going to add a class here called tests. I'm just going to minimize some of this stuff. I'm going to make that class public. And then I'm going to add a few benchmarks in here. So I'm going to take this source and put it here as a member of this class. and I'm going to add a benchmark. Oops, benchmark. This is an attribute that comes with benchmark.net. I just write a function that's attributed with this, and I'll call this sum compiler. And here I'll say in sum equals 0, and then for each int I in select compiler with my source, and I'll just keep it simple and do I times 2 and return. And the reason I'm just trying to do something with the data, something super cheap that won't perturb my numbers too much. But this way I can be sure that it's used and I can return the value to ensure that it can't be removed. So I'll just do that for compiler. Great. Okay. So we have a benchmark for the iterator. Mm-hmm. Let's just copy and paste that, and we'll do the same thing for select manual.
Yeah. So we're going to. I love how benchmark.net implements things as an attribute like that, because if you're used to writing tests, now you're used to writing benchmarks. And here,
these are performance tests rather than functional tests. And in fact, we use benchmark.net for all of our performance tests with .NET Runtime. And there's a repo you can go look at, .NET/performance, which contains all of our regression performance tests. So multiple times a day, we're running all of those tests across x86, x64, ARM, ARM64, Windows, Linux, Mac, a whole bunch of different systems, and just making sure that nothing gets slower, and if things get faster, we know about it. So we rely heavily on this. Let me actually add one more, and I'm just going to add one for LINQ itself. So let's call this sum LINQ. And then instead of select compiler or select manual, we'll do enumerable.select. So the real select. And you talked about attributes, Scott. I'm going to add one or maybe two more attributes up here. The first is I can ask benchmark.net to collect additional information. I'm going to add what it calls a memory diagnoser. It's got diagnosers, which are basically plugins, that allow me to track and report additional information. And one of those is about allocation. And then because we're doing sort of a live demo, I'm going to add one more, which is called short run job. By default, benchmark.net likes to take its time and do a ton of runs and do a lot of analysis on those runs, kind of get things down to a very statistically significant value. Because I don't want to make people sit here and wait for a while, I'm telling it, just skimp. Do a little bit less just to make this take less time.
Now, I had a fanboy moment where I mentioned how great the memory allocation and profiler stuff was on Visual Studio. Where do I file away memory diagnoser and what it does around allocations and its understanding of allocations with the IDE's tools around memory allocation?
Yeah, great question. Think of the IDE's tools as like the super deep dive to be able to nitpick and examine individual things and dive in and look at back traces and where did this allocation come from and how big is it and what does it contain and whatnot. The memory diagnoser with benchmark.net is about giving you a top level number that you can think about, or a few top level numbers that you can think about. How many GCs were performed? How much did I allocate? Such that if I make a change to my code, and then run my perf tests again, I can see maybe the total amount of allocation dropped. But I'm not diving into the specific details. Benchmark.net does actually have the ability to, you can add additional diagnosers that are able to capture performance traces that you can then open up in tools like Visual Studio or Purview so that you can actually capture them as you're doing your benchmarking. But I'm just using this sort of simple memory diagnoser for this purpose.
We had used a prefix that, again, may not be familiar to folks that whether they speak English fluently or not, when we said, Heisen this or Heisen this, Heisenberg, the Heisenberg uncertainty principle is this idea that if you observe something, you may change it. So then how do you get real numbers? I look at something. And I go, I looked at it, but it knows I was looking. It saw that I was looking. How do we think about that in the context of benchmark.net?
This is one of the things that I love about benchmark.net.
It's there.
It a lot of the effort that has been put into it has been to reduce the noise that you're talking about. So, for example, we'll come back to that in 1 second because I can show you exactly what I'm talking about.
Perfect.
We have to write one more line here. We say benchmark. .NET switcher, or benchmark switcher rather, and we tell it I want to run all all of the tests that you can find throughout this whole program. So there's a type in this assembly called program. So any test that you can find, any public type that has a benchmark, I want you to run that.
Okay.
So I build in release, and then I run. And as soon as this builds, I'll bring over the window. You see it asks me, which benchmarks do you want to run? I'm just going to say, the ones that you know about. And what I wanted to highlight is that once it gets going, right now it's building multiple applications, basically taking my code and building it into different applications so it can fine tune what it measures and make sure that it's able to measure with as little overhead as possible. And part of that is as soon as it starts running, you see how it says overhead warm-up, overhead actual, workload warm-up, and so on. So it's actually measuring even things like how long did it take to invoke an empty function with the same signature as my benchmark. And then it'll run my real benchmark with the full code, and it'll subtract effectively one for the other. So it's trying to remove all of that overhead it possibly can. So we got back our numbers. Now I mentioned this is a short job, so take the numbers with a little bit of a grain of salt. There's a little bit more give and take. And you can see that our compiler and manual numbers here are really close. In fact, if you divide this, I think I was doing 1,000 iterations effectively. So if you divide 6 microseconds by 1,000, you're at 6 nanoseconds. And that means the difference between our compiler and a manual per iteration was 1 nanosecond. That's kind of inconsequential. That's kind of noise. Although you do interestingly notice that our manual implementation does now allocate a little bit less than what the compiler does. And there's actually an open issue on this on .NET Roslyn for ways in certain cases where one of the objects is larger than it needs to be. So hopefully that'll be addressed.
And to make sure that the point wasn't missed here, that US, that's not a millisecond, right? That's a microsecond. So that's not a thousandth of a second. It's a millionth of a second.
Exactly.
Yeah.
So these numbers are super close. Showing that the compilers, the iterator version and the manual version that we wrote are super close. Interestingly, the one built into Enumerable is way faster and way smaller. And there's a very good reason for that. And we can see it. I won't dive in too much because we're basically out of time. But if I come in here, I printed out a type earlier. If I print out select... what do we call it? Tests, right line, tests dot, these need to be public. Public. If I print out select compiler on, doesn't matter what I do here, array dot empty of int I to I, and I do the same for manual, and I do the same for enumerable dot select. I'll put this one at the bottom just for fun and run this. So we can see the compiler generated one has its beautiful, the beautiful compiler generated name, which is mangled based on the type that it's in, the method that it was in, the nested method that it was in, and so on. We can see our type is. Actually, I can't use my choice of array.empty was a poor example. Let me just pull this back up. It
looked like it got optimized completely away there for a second.
Yeah, exactly. Let me put this right here. Although it's close to nature what I wanted to show, but there you go. You can see we've got my manual one, and then we have the one from LINQ. And you can look at the name of this type and kind of get a sense for why it might be faster. This wasn't.
Can I guess?
Yeah.
LINQ realizes that there's regular stuff that people would be doing this on, so it has optimized implementations for different types.
Exactly. So you see it says array right here. If I were to come back into my program, I'm just going to duplicate this. Let me do it for new list of int. And let me do it for new queue of int. And I'll do it for enumerable dot range from 0 to 1,000. And I could do more and more. When I run this, We can see there was one for array. There was one for list. There was one for an enumerable that I didn't quite recognize, but it's still an enumerable. There's one for range. There's a list of these things that the implementation is special casing and saying, I'm going to generate a special implementation for arrays. I'm going to generate a special implementation for lists. And one of the things that we didn't quite get to is you can actually chain. LINQ is actually able to chain information between. So if I add one more of these, and I'm just going to write it with sort of a little bit cleaner syntax. Let me just say source, console.writeline source.where I mod 2 equals 0 dot select. Doesn't matter what I'm doing in my delegates, and I printed that out. You can see now we actually have a single iterator that is a where select iterator for arrays.
Now I'm wondering, are there dozens of these? Like, what qualifies one to like need a custom one? But it makes total sense now, because if I were going to work on the team and I'm like, we do some thought and we think, well, X number of percentages of people who do this are using select range. We should make those people more successful. What's the best way? Custom iterator.
Exactly. And we're looking at, we look at data. We have a variety of data sources available to us. So one of the enterprising developers on the team basically cataloged everything that was appropriately licensed on NuGet and looked to see what are people actually using. You can break open the data, and so we can see like what are any enumerable.any is the most popular LINQ method. Select is very high up there. Select where followed by select. Order by followed by take followed by or order by followed by skip followed by take. We can see these combinations and we can optimize these patterns by flowing this kind of information. So this iterator isn't just something for select that recognized that the source was where. We actually saw when you called select, we see, oh, the previous one was where. Let's grab its filter. And so now this is its own standalone iterator where in its tight loop, it will run the filter directly and it will run the selector directly rather than having to call back through some arbitrary implementation of the interface to get back to the previous thing. And it's not just about special iterators as well. We can specialize things. For example, if you call order by min or order by first, rather, we can just turn that into a min. We don't actually have to do a full sort. We can just find the smallest thing.
Right, because you know more stuff. You have context.
We have context as it flowed through. So this is actually one of the reasons why, if you, or probably the main reason why, if you look at the LINQ code base, waving my hands, probably 50% of the operators are implemented with iterators, and approximately 50% are implemented manually. And we implement them manually specifically so that we can flow additional information between the operators to special case various patterns.
So how hard would it be? Again, I think we're going to do a part 2. How hard would it be for us to then notice that in our implementation? We don't have to make dozens, but if we made like an array specific one to make our, could we be as fast as .NET?
We can, and let's do that next time.
Okay. So this is fantastic. Next time on Deep.NET, we're going to take this chunk of code here. I just named the show. We're going to take this chunk of code here, and we're going to find out what we can do to compare how we just saw that we were allocating more than the iterator. We fixed that. We did a benchmark. Now we can go and see if we could specialize our implementation of select for different inputs, including arrays, and then potentially be as fast as the .NET implementation. Would be pretty
like I'm on a soap opera.
When left, we left our heroes. Yeah.
As the .NET turns.
Exactly. All right. If you like this content, share it with your friends, because we're having a blast, but we need to know that folks enjoy this work, because we're taking up Stephen's time. And then if there's other topics you'd like to hear and other engineers you'd like to hear from, put those in the comments. And as the kids say, smash that bell, subscribe, like and subscribe, and we will see you again another time. Thanks a lot, Stephen, for your time.
Thank you, Scott. This is great.
Because the kids say that.
You make me laugh.